Hey, well, thank you all for coming in person and on Zoom today. I'm Megan Doherty, Director of the Museum of the White Mountains. It's great to have you join us today. As we gather today, we're all on Indigenous lands. Those of us at the Museum of the White Mountains are on Indokina, which is the ancestral and present homelands of the Abenaki and Wabanaki peoples. We're grateful for their stewardship of these lands and waterways. For those of you on Zoom, we've put some links in the chat where you can learn more about the Indigenous histories of your place at native-land.ca, as well as the Abenaki peoples of the Northeast through the Musée des Abenaki in Quebec. Today, as we learn from climate scientists about our changing planet, I hope we will think about how we too can be good stewards of the land and waterways we call home. So I was delighted when Andrew Williams reached out to see if we would host an event with Climate Up Close during their New Hampshire tour this summer. They're climate scientists committed to making the essentials of climate science accessible to a broad audience. They strive to build trust and partnership between the scientific community and the larger public they serve. As a museum about a place that has had damaging torrential rains this summer, as well as less snow in winter, I'm always looking for ways to share what is happening around us in an accessible manner. So they seemed like a perfect fit for our programming. Please join me in welcoming Climate Up Close.
Thanks, Megan, for the lovely introduction, and thanks everybody today for coming out and to the museum for hosting us. As Megan mentioned, we're Climate Up Close. We're a group of volunteer climate scientists who are passionate about spreading the message on climate change. And I just want to clarify what we're not. We're not a super PAC. We don't accept any government funding. We're really a ragtag band of climate scientists who, to the extent that we're funded by small donations from individuals. And I'll let the other group members introduce themselves as they come up, but my name is Nathaniel Tarshish. I've learned from my colleagues that there's actually a debate as to whether I have a PhD. I filed it last week, but I won't get the degree till next week. So you can call me Mr. Tarshish or Dr. Tarshish, it's up to you. And the origins of the group actually go back 5 or 6 years ago at the beginning of my PhD when I was first learning the science. And at that time, I got this sense that the national conversation was increasingly diverging from the scientific consensus. So the conversation that was happening on the airwaves or around the kitchen table felt like it was out of touch in important ways. And because what we choose to do about climate change or not do will have immense consequences, we all felt motivated to get out there and to hold conversations like this with the public. And so far that effort has taken us around the country. Our first tour was in central Pennsylvania. We've been down to Florida, last year was in Chicago, and we're thrilled to be here in New Hampshire. This is our second day of touring, and we'll be here through the weekend. So if any of your friends couldn't make it today, just direct them towards our website, climateupclose.org. We'll flash that at the end of the talk, and we have five or so more events in the area. Okay, so I mentioned this national climate conversation, which oftentimes can be frankly confusing. And I wanted to check in on it, to sample it, basically, and with 3 representative quotes. We're going to start off here with Kathy Popkins. This quote is not attributable to her, but heat waves in the US are now no more common than they were in 1900. And that was said by Steve Koonin. He's a physicist who served as the Undersecretary for Science at the Department of Energy in the Obama administration. And he's a prominent academic who also authored this recent book, which has been getting a fair amount of press. It's called Unsettled: What climate science tells us, what it doesn't, and why it matters. Okay, here's another view that I think is floating around. Let us be clear, Hurricane Dorian has everything to do with climate change. And that's actually your neighboring senator, Bernie Sanders. And then finally, the world is reaching the tipping point beyond which climate change may become irreversible. And that's Kofi Annan, the former Secretary General of the United Nations. Okay, so 3 differing views there, and perhaps some of them struck you as right on the money, and maybe other ones seemed frankly out to lunch. But what you might be surprised to find out is that as climate scientists, we would not fully endorse any 3 of these statements. In fact, each one contains a kernel of misunderstanding about what the science can and cannot say. And so our goal today, more broadly, is to communicate the landscape of climate knowledge. So what's settled science? What do we have really high confidence in and we've worked out? What's on the boundary? What are the topics we're currently working on? And what's uncertain? What do we have not that much concrete to say about? So that's what we're going to start off with today, and I'm going to welcome up Andrew to outline some of the settled science.
Thanks, Nathaniel. So yeah, my name's Andrew Williams. I'm a climate scientist at Princeton University. And you may already be able to tell that I'm not from the States. I spent a lot of my life outside the States. Particularly, so I grew up in the United Kingdom, in a small country called Wales. And this is a photo that I took a couple of years back on a hike in the valleys, which is the region in the south of Wales. You can see these nice valleys here, near where I grew up. And the reason I'm showing this is partly because it's nice to know a little bit about each of us as people, but also because my eye is drawn straight away to these beautiful fluffy clouds. And I spent a lot of my time growing up, clouds, like just staring at clouds, lying on the trampoline, just watching them going past. And I love them for their beauty, you know, for the fact they were so complicated and I didn't really understand them. But they felt important, you know, you get rain from them and this type of stuff. I was also really into science. I went to university in the UK in Oxford and I did physics. And part of the way through my undergraduate, I discovered that all the physics that I was learning that I was really excited about how quantum mechanics and light and the motion of fluids, clouds are just basic manifestations of all this physics I was learning in university. And at the same time, I was learning that clouds are one of the most important aspects of climate change. So one of the reasons that projecting future climate change is such a hard task is because clouds are really hard to understand. And so that led me into climate science. I did my PhD and now working here in the US. So that's enough about me. Let's talk about what aspects of the science of climate change do we think are settled. So the first thing that we want to talk about in this regard is the atmospheric CO2 concentrations. So we've been measuring these directly since the 18th century, and you can see that since this period, with the dawn of the Industrial Revolution, there's been a steady uptick of CO2 in the atmosphere. From pre-industrial times, we were about 280 parts per million, ppm, up to 420 roughly parts per million in the present day, about a 50% increase. And you can see that around 1960, there's a really, from this period, there's a really rapid uptick of CO2 of about 2 ppm per year. And sometimes you see people kind of saying, oh, you know, parts per million, that means that if you take a flask of air, then for every million molecules of air, there are only about 300 or 400 molecules of CO2. That doesn't feel like very much, and that's something that can sometimes confuse people. But one thing that I would ask is, who here drinks coffee? Too much coffee? Yeah. So the amount of caffeine in coffee is about 300 parts per million. So the active ingredient in coffee that our body is detecting, that our body craves, is about this amount. So if you've ever been able to detect the difference between a caffeinated cup and a decaffeinated cup, you felt the impact of 300 parts per million of something. So that's just a nice little number to keep it, a nice little tidbit to keep in your mind. And this is just measured. This is just an observation that we have. At the same time, we have observations of global mean temperature going back to pre-industrial times as well. So from about 1850 up to present day, in the global average, we've had about 2 degrees Fahrenheit of warming. And this black line here, the center black line, is the globally average temperature, and this gray shading gives you some sense of the uncertainty in that number as we go backwards in time. So as you go down to like 1850, there's a bit more uncertainty about what the global mean temperature was because we weren't having measurements around the Earth. As we've started to have more stations, and particularly since we've started to have satellites, which can help us measure this as well, we have really tight constraints on this global mean warming. So these are two things that are just observed. There's no model that's going into this. You can just have a thermometer, have a flask of air, and get these things. But how are they connected? So to connect these two quantities, changes in CO2 and global mean temperature, we need a climate model. And a climate model is basically a few million lines of computer code that you run on a supercomputer. And the way you build them is you take all the physics that you know, all the science that you know about Earth's atmosphere, so how air moves around on a rotating sphere, how light gets transmitted up and down through the atmosphere, how clouds form, how rain forms, and you just run that on a computer, and you can run these climate models, but only tell them that natural things have changed over the historical period. So by natural, I mean things like the solar cycle and volcanoes. So, and if you run a climate model with only giving it natural changes over the historical period, you see that you don't match this long-term trend. So you get wiggles. So in particular, you can see here around 1990, there's this really strong cooling of the planet when you have natural changes. That's, anyone want to guess what that is? Anything happened in 1990? That was Pinatubo, big volcano that went off. And so volcanoes tend to cool the planet. And so when you give a model like this, volcanoes, it's able to reproduce these dips that have happened in the past with volcanoes, but it's missing this long-term trend. We can run this exact type of model again, but include both the natural changes and changes in human emissions of greenhouse gases and aerosol. And when you include human-induced changes, you get a really good match to this long-term trend in temperature. And this gives us some confidence that these changes in temperature we've seen over the historical period are driven by CO2 and by burning of fossil fuels. So this is a global mean picture. So you just got one number at each year, but you can also look at the pattern of warming. So obviously, warming in different places doesn't always need to be the same. So this is the change in warming over recent decades. So red means that over this period, 1980 to 2020, regions have warmed, some regions have warmed more and some regions have warmed less. And if there are no dots, it means that we're confident about that change. And there are three things I want to point out about this map. Firstly, is that warming is enhanced over land. So you can see here, if you look over the continents, you have more darker red colors than you do over the ocean. Another aspect which I want to point out is that warming is enhanced in the Arctic. So these dark red colors up here show you that there's been a lot more warming over the North Pole than there has been over the other parts of the world. This is called Arctic amplification. You've heard this in the news sometimes. And then another aspect of this map is that there are weaker changes in warming over the Southern Ocean. These are three aspects of climate change which stand out really well or really strongly in the data. And it might be interesting to know that, so these are changes from the 1980s to present day. At the beginning of this period, people were running climate models already and already predicted these things happening. So climate models have predicted already, before we were able to see this in the data, things like the land-ocean contrast in warming, so land warms more than the ocean, this Arctic amplification, and the weaker warming in the ocean over the south, near the South Pole. So the fact that models are able to not only get this global mean temperature right, but also the spatial pattern of temperature changes correct, gives us confidence that we can use them to understand climate change. So we return back to this landscape of climate knowledge that Nathaniel introduced a second ago. We can put CO2 increases driven by human activity and their link to global mean temperature increases and the pattern of warming in settled. We've got a strong scientific consensus that this is settled science. So what are some impacts that are settled? So we've talked about just changes in global mean temperature. How do these impact things that we care about more day to day? One natural one is heat waves. So there was a heat wave in New Hampshire last month that broke records. I don't know if any of you were around for that and experienced that. But in general, over the historical period, heat waves have become about 3 degrees Fahrenheit warmer. And that 3 degrees Fahrenheit is coming from the 2 degrees Fahrenheit we've had in the global mean in that line plot, coupled with the fact that land, which is where we all live, has warmed faster than oceans. That's where you get this 3 degrees number from. And so In pre-industrial times, what would have been a 97-degree heat wave is now in present day, on average, a 100-degree heat wave. And this is in the average global mean sense. We can also look at the pattern of this as well. So this is a plot from the IPCC, which is the Intergovernmental Panel on Climate Change. So some of you will be familiar with this, I'm sure, but the IPCC are basically a group of scientists that come together every 7 or so years and assess the state of the science and try to form a consensus of what we think is happening. And they may also make these maps, which are called hex maps. So each of these hexagons represents a region on the Earth. So these 4 ones here are the different parts of Australia. This is New Zealand, Madagascar, Africa, South America, and North America in this top left corner. And the color of these hexagons tells you whether heat waves over the historical period have increased or not. So red means that in the data, we can see that these heat waves have increased. And the number of dots in these hexagons tells us how confident we are that that change is coming from human activity. So 2 or 3 dots tells us that we're confident that that change is coming from human activity. And the main thing to point out, which is pretty obvious from this graph, is that almost everywhere in the world is red, and the vast majority of places have either 2 or 3 dots. So that tells us that heat waves have intensified across the world, and we're very confident that can be attributed to human-induced climate change. Now with this knowledge from the IPCC in mind, we can revisit this claim from Steve Koonin, which is that heat waves in the US are now no more common than they were in 1900 from this Unsettled book. And what he's doing here, so he's not incorrect. So you can see that Central North America and Eastern North America here are 2 of the only places on Earth where the data is not yet sufficient to tell us whether heat waves are increasing or decreasing. But in the book, he points this out and ignores the rest of this picture. So it's just cherry picking. Sometimes you'll find that people focus on the exception rather than the rule because they have some point they want to get across, or they may be acting in bad faith. Another subtle impact of changes of global warming is changes in sea level over the historical period. So since about 1900, we've had roughly 3 inches of global mean sea level rise. This is a picture from New Jersey of the coastal flooding that happened during Hurricane Sandy. So there were storm surges of up to like 10 feet in places. And in coastal communities, changes in sea level rise can be one of the most consequential impacts of climate change. So where does this 8 inches come from? So roughly 5 inches of it is coming from the melting of ice. So this is land ice. So for example, the melting of glaciers in the mountains, and also from the melting of ice sheets. So the Greenland and the Antarctic ice sheet. So that gets us, most of the way there. Where's that other 3 inches coming from? It turns out that this other 3 inches of sea level rise is coming from the thermal expansion of water. So this is the same thing that happened. So when water warms up, it expands. It's exactly the same as a thermometer, the mercury in your thermometer. So when you have a fever, you put it in, the mercury expands and it tells you the temperature. That's why it moves up the thermometer. The same thing is happening here. We've warmed up the planet, the ocean is taking up energy, and heat is going into the ocean, and it's expanding. And these are 2 things that we can really robustly link to global mean temperature changes. So again, we return to this landscape of climate knowledge, and we're looking at this settled part here. We can add heat waves and a gradual rise in sea level to the settled category of the science here. And now what we're going to do is we're going to move on outside of settled. We're going to move on to this barrier and into the parts of climate knowledge which are uncertain. And for that, I'm going to hand over to Aaron.
Thank you. My name is Aaron Match. I've loved the weather for a very long time. When I was in kindergarten, I used to wake up before my parents and 3 siblings, go outside to the driveway, get the newspaper, bring it inside, open up to the weather page, cut the weather page out of the newspaper and put it in an archive that I had in a little cubby. When my family would wake up, my parents would come down and they would have to ask, okay, what's the weather going to be? And then I would take the weather out and show them what it's going to be. I also love playing outside. This is a picture from my front yard in Harrisburg, Pennsylvania. This is Snowhenge is what we called it. And I wanted to know what was the weather, what were the forecasts? I was very interested in understanding, predicting the weather, and that grew into an interest in climate. And I'm now a researcher of climate at New York University. And today I'll be talking, as Andrew said, moving into the periphery of what climate scientists know, what is at the edge of our knowledge, and beyond into what is uncertain. So let's start. Often when we experience heavy rain, as New Hampshire experienced some significant heavy rain this year, there's an understanding that there's a connection between that heavy rain and global warming. And the connection is quite natural to make. We do expect that heavy rain intensifies by about 4% per degree Fahrenheit of warming. And this is a picture from, is there a way to hide the?
Yeah, I think click on the 3 dots.
3 dots. So it disappeared.
Yeah,
Yeah.
there we go. Sorry.
Thank you.
I think that they,
Oh.
there, it just, great.
Cool. Okay. This is a picture from northern New Hampshire early this year from Hurricane Beryl. So we expect, climate scientists expect heavy rain to intensify by 4% per degree Fahrenheit. But it's actually heavy rain is very noisy and splotchy, the places that it happened. And so when we look into the records to see how heavy rain has changed, it's actually very hard to detect those changes. And so Andrew showed a plot of how heat waves have been changing, and that plot was all red and all 3 dots, showing very high confidence that global warming is exacerbating heat waves. This same plot for heavy rain, now green means that heavy rain has increased, but you can see it's much less of the plot is in green than Andrew's was in red. And there's almost no places that have 3 dots. Most of this is actually quite uncertain. And so the connection to heavy rain is more on the boundary of our understanding of climate change. One of the most significant manifestations of heavy rain is hurricanes, and hurricanes are often also discussed in when we try to make sense of what global warming is doing to human life. And there are 2 settled ways in which hurricanes should be affected by global warming. So the first one is that we do expect rainfall in hurricanes to intensify by this 4% per degree Fahrenheit of warming. The second way that global warming exacerbates hurricanes is that when hurricanes make landfall, they have storm surge flooding. But now, thanks to that 8 inches of sea level rise that we have from global warming, that storm surge flood is going to be 8 inches higher. So those are 2 settled ways that global warming is understood to affect hurricanes. But our overall global picture of how global warming affects hurricanes is actually more mixed. And this might be come as a bit of a surprise, but that uncertainty comes from the fact that climate scientists don't know how the number of hurricanes will change in response to global warming. Some of our most credible climate models, the same tools that we use to understand that the past temperature change, some of them predict that we'll get fewer hurricanes as a response of global warming. Some predict that we'll get more, some predict no change. And due to that uncertainty about how the number of hurricanes will change, and when we look into the past and we see that there actually have not been any measured increases in the number of hurricanes. Here's a look at landfalling hurricanes in the United States over the past century plus. There's no significant change in the number of landfalling hurricanes. For those reasons, due to that mixture of confident and less confident information, we're going to put hurricanes and heavy precipitation on the boundary between settled and uncertain. And so then we can return to the quote from Senator Sanders. He said, "Let us be clear, Hurricane Dorian has everything to do with climate change." This quote overstates the connection between climate change and hurricanes. There are 2 other impacts that are often discussed in the public conversation that are also on the boundary, and that's droughts and wildfires. I'm not going to go into more detail here. At the end of our talk, we'll have a Q&A. If you want to know more about why we put these on the boundary, please ask. Now we're going to move from the boundary of knowledge out into the wild west of what is even more uncertain. And if you thought hurricanes were scary, And some of the things out here might be even scarier, and those are tipping points. Who has heard of tipping points? Yeah, almost everybody. Two of the biggest tipping points that get discussed, here, the first one is West Antarctic ice sheet collapse. Okay, we've had 8 inches of sea level rise observed, but there's a huge amount of ice in the West Antarctic ice sheet, which scientists have identified as being potentially more vulnerable to global warming. And there's 2 ways that that ice could plausibly contribute to sea level rise. The first one is what we've seen so far, which is gradual melting that has from throughout the globe, of ice throughout the globe that has led to that 8 inches of sea level rise that we've seen. But there's another way that ice could contribute to sea level rise, and that is a type of collapse, kind of like picture a sandcastle on the beach getting hit by waves and chunks of the ice just getting pulled into the ocean. And the West Antarctic ice sheet has enough ice in it that if it were to collapse, it would raise sea level by 10 feet. So this is something that scientists need to take very seriously, and they are. When they assess the plausibility of these mechanisms for that sandcastle collapse, the most credible assessment of their plausibility is that they are poorly understood processes of instabilities characterized by deep uncertainty. This does not mean we should ignore these prospects. It means we need to dig in to understand them better. But if somebody was perhaps being kept awake at night for fear that this ice sheet was already committed to a fast, abrupt, irreversible collapse, then this would suggest that actually the situation is much more uncertain. What about the second one, the permafrost carbon bomb? So permafrost, that's permanently frozen soil around the Arctic. There is a huge amount of carbon frozen and locked up in that soil that has built up over thousands of years. And there's enough carbon in that soil, there's twice as much as carbon there as there currently is in the whole atmosphere. And if it were to all be released from that soil, then it could increase the temperature of the globe by 6 degrees Fahrenheit. So there's a huge amount of carbon there. And what scientists fear, and what has been discussed in the public conversation, is that as this soil thaws, as it warms and thaws, microbes could start eating that carbon that used to be frozen and emit that carbon as CO2 to start being a warming gas. And that extra CO2, in the worst case scenario, could lead to more warming and more thawing and more emission of CO2 in a runaway feedback. And so that's a really nightmare scenario, a carbon bomb. What does the IPCC have to say? They assess it as being a significant but still modest 1 to 7% effect. That is the amplifying effect of this feedback on the warming that we have. And they assess it as being not enough to lead to a runaway warming situation. So it's still deserving of further research and not to be ignored, but in no sense have we already committed to some of these nightmare feedback scenarios. And because we know we haven't committed to them, we can return to the third quote of the talk. The world, Kofi Annan said, the world is reaching the tipping point beyond which climate change may become irreversible. There's no evidence that the world has reached a tipping point. There's no evidence that the particular temperature targets that we have politically committed to, for example, the Paris target of 2 degrees Celsius of global warming, there's no evidence that that is a tipping point. And so tipping points are very uncertain and very speculative parts of the landscape of climate knowledge. They're all the way out here. And having put tipping points now on this landscape of climate knowledge, this now completes today's version of our landscape. We'd be happy during the Q&A to fill in other parts that you might have questions about. And so now we can step back and assess what this says about the conversation. So you see that some of those nightmare scenarios are very far out on the speculative part of our landscape. What you can also see is that the quotes that we selected and have been considering throughout the talk, what those speakers did was they took an impact from one part of the landscape and they represented it as if it was in a different part. They scrambled up the landscape. And that really gets to us when we're trying to make, we're scientists trying to really make sense of what we know and what we don't know. And we see that conversation misrepresent what is known. Okay, so Steve Koonin would have you believe that heat waves are a very uncertain impact of global warming, when in fact, throughout almost the whole globe, we have quite confidently attributed heat waves to global warming. Senator Sanders suggested that hurricanes had everything to do with climate change when our understanding remains more mixed. And Kofi Annan suggested that tipping points were a settled part of the climate impact. And so we hope up to this point in the talk that we have equipped you to unscramble the landscape of climate knowledge, and you can use this to help parse the climate conversation as you hear it. So now, having finished talking about the landscape of climate knowledge, we're going to pivot to the next part of the talk. And for that, we'll have Dr. Nadir Jeevanjee.
Hello. Good afternoon. Let's see here. This works. So I'm Nadir Jeevanjee. I'm a staff scientist at a federal research lab in Princeton, New Jersey. And our lab actually builds climate models. It was actually the first, it's called the Geophysical Fluid Dynamics Laboratory. And we were the first climate modeling center in the world, actually. So we build the climate models that you guys have been hearing about and some of the data that you see. I'm actually, even though I live in New Jersey now, I'm a native Californian, born and raised in Los Angeles. I went to grad school at UC Berkeley, pictured here. And yeah, some of you recognize that. Excellent. And I started off my scientific career as a theoretical physicist. So went for a PhD in physics at Berkeley and was interested in esoteric topics like quantum gravity, how to reconcile quantum mechanics with Einstein's theory of general relativity. And the arcaneness of that pursuit is even symbolized by this little ivory tower right here. But eventually I wanted to do something more down to earth and turned to studying the atmosphere and climate. So now that we've thought about the various impacts of global warming and how certain they are or aren't, I want to turn to a slightly different topic, which is how our actions shape what's to come. And to kick off that discussion, I want to ask a very simple question and poll you guys quickly. If we stopped emitting CO2 tomorrow, we shuttered the power plants, we parked all the cars and trucks, we stopped our CO2 emissions, what would happen to global temperatures? So I'll ask this question with a graph. Here's temperature change on the vertical, time on the horizontal. Here's the temperature change we've had up to now, about 2 degrees Fahrenheit. So if we stopped emissions now, would the temperatures continue to increase because of, say, some committed warming, some warming in the pipeline? Or would temperatures stay flat for some reason for a while? Or would temperatures decrease and go back to their pre-industrial level because the Earth is returning to equilibrium? So how many people think A, we have committed warming and the Earth would continue to warm? All right, good, thank you. Anyone for B, temperatures would stay flat and remain the same? Okay, we've got one. And anyone for C, temperatures would return to their pre-industrial level? No one for C, okay. So A is a common answer. But in fact, some fairly recent climate science from the last 15 years or so tells us that the answer is actually B, that once we stop emitting, temperatures actually stay flat for a long time. And this is true whether we stop emissions today, or say when we meet the Paris target, or even in a scenario where it's more of unabated emissions and we warm a lot more. But no matter when we stop emissions, temperatures will stay flat. And this fact, which I said is a fairly recent discovery of climate science, has actually had profound consequences. It undergirds our current climate policies. This leads to the whole notion of net zero, where we have to get down to zero emissions. Otherwise, if we keep emitting, keep going up. But zero emissions are enough to stabilize climate. That's what this is telling us. And it leads to the notion of a carbon budget. And that's governing international negotiations right now. I believe it also has consequences for how we think for just how we as humans and as a society think about climate change. And I think there's two consequences here. One is more of a glass half full perspective, which is that if temperatures stay flat when we stop emitting, then any future temperature comes from future emissions. And so that kind of tells us that the future is up to us. Sorry. Is there a way to, let's see. Here.
The mouse down.
I'll go away. Go away. Okay. Well, so you can't see it here, but we call this fact the post-emissions plateau. That once you stop emitting, you get a plateau in global warming. And one of the consequences is that future warming comes from future emissions. So I find that empowering. So that's saying that the future is up to us. If it warms in the future, it's going to be because we have, thank you, Andrew. We have chosen to emit more. At the same time, if you look at the horizontal axis here, the timescale of this is centuries to millennia. So whatever warming we do have, it's going to be with us for a long time to come. And so the climate future may be up to us, but this future is long. Let's see here. Oh, it's not clicking anymore. There we go. All right. So the future emissions, what kind of trajectories, what is our trajectory been so far? And what are some alternative future trajectories? So here are our historical emissions, starting kind of at the start of the Industrial Revolution, going to the present day. Emissions are in gigatons of carbon per year. So gigaton is a billion tons, just like a gigabyte is a billion bytes on your computer. We've got a little over 10 gigatons of carbon per year emissions today. And in a more of an unabated emissions scenario, these emissions continue to grow throughout the 21st century or leveling off somewhat. If we wanted to look at a scenario that is consistent with, say, the Paris target, limiting warming to 2 degrees Celsius, what does that look like? It looks strikingly different. It looks something like that. We basically, instead of continuing to increase our emissions, we would have to abruptly start to decrease them. And we could emit a little bit more until we got to about 2 degrees Celsius of warming, at which point our emissions would have to go to 0, so that then the temperatures would just flatten out. And so you see, it's a pretty stark contrast between business as usual and what's required to meet the Paris target. So this is a very tall order. Where are those emissions coming from? So here's a breakdown by country. And you see that, sort of in the latter half of the 20th century, the USA was dominant. But at the turn of the millennium, things have changed a bit with the rise of the Chinese economy. And now they're, more than double our emissions. And if you look actually, right at the sort of present day, this chart only goes up to 2022, a lot of the growth globally is now actually coming from India, which you see is just starting to rise. China's starting to flatten out just a teeny little bit. And so where our emissions come from is really changing over time, not just as populations grow, but as developing economies develop and as the lifestyles of other people approach the lifestyles that we enjoy here in the US.
You want to sit over here or not?
So what about our consumption here in the US? Here's a very engaging pie chart.
Program.
And kind of the moral of this pie chart is that our emissions kind of come from across domains of life and across activities. So there's transportation, of course, our cars and our trucks. That's a CO2 emissions that we're sort of very in touch with. We hear a lot about, we may think a lot about. Certainly electric power generation, right? Coal plants, natural gas plants. That's another huge chunk, about a quarter. About a quarter also is industrial fossil energy use. So this is applications that maybe as consumers we don't see every day, but steel production, smelting of aluminum, other industrial uses where you need high temperatures for industrial processes, and so you're just burning fossil fuels on site to generate high temperatures. That's a surprisingly large piece of this pie. Agriculture is a significant piece of the pie. These are both, we use fossil fuels in our fertilizers. There's methane emissions from cows and other ruminants. Those all go in here. And then our energy use in fossil fuel energy use in buildings, right? We pipe in natural gas into our furnaces, into our water heaters, into our gas stoves in our homes. This is also a significant chunk. So you see that fossil fuel use is really embedded throughout our daily activities, maybe in ways that we don't always see or acknowledge. And that also speaks to the trickiness of the problem. And there are solutions around electric cars, renewables, potentially hydrogen for industrial uses, changes to our diet. But fully, shrinking these pieces of the pie down to net zero, again, is a tall order. And so far, we've made some progress, but there's still a long, long way to go. And that sort of leads me to the sort of final message of our talk, which is that even if we understand the science better and we can put this diagram in its proper order and have a sense of what's settled and what's uncertain, there's still so many questions about our own actions and our sources of emissions and what we're going to do. And science, of course, has to inform that conversation, but it cannot tell society what choices to make because those choices involve our values. So here's some examples, for instance. Should developing nations be allowed to develop via fossil fuels, cheap and easy fossil fuels the way that we have, or should they be expected to develop via renewables? That's a conversation that has to be had and is being had right now. And there's cases to be made on both sides. Should we here in the US say, should we prioritize adapting to the climate change we already have and that's coming down the pike, or trying to mitigate further climate change? So this is a seawall that's been built outside of Venice, Italy, and to adapt to current and imminent climate change. And switching to renewables is mitigation, trying to reduce further climate change beyond what we're already committed to. If we do decide to mitigate, that'll require policy. And what should that policy look like? Should it be composed of regulations, standards that we have to adhere to, and we might be penalized if we don't adhere to them? Or should it most be carrots, incentives, like in the current Inflation Reduction Act, which offers rebates and subsidies for buying an electric car, for converting your gas appliances to electric appliances in your home? Right? Again, this is a question that we all need to weigh in on about how do we want to do this. And finally, and perhaps most controversially, there's proposals to geoengineer to offset global warming. How many people have heard this phrase, geoengineering? So this refers to active and intentional human intervention in the climate system to offset our inadvertent warming of the climate. So examples of this include injecting reflective particles into the stratosphere to mimic the cooling action of a volcano that Andrew told us about. Other proposals involve spraying particles into the atmosphere above the oceans to artificially brighten clouds so that they reflect more sunlight. This is part of why clouds are so important for climate change, is because they reflect a lot of sunlight. Small changes in clouds can have an outsized impact on climate. There's also proposals and even test sites for just pulling carbon dioxide directly out of air. This is called direct air capture CO2, where you set up giant banks of fans, have air flow over a chemical bath, and you absorb CO2. And so each of these actions that we're talking about here require energy, time, resources, money, and there's trade-offs involved with all of them. And so we have to come together as a society to make decisions about this. And of course, the science plays a role, but our values and priorities do too. And so hopefully with that, after a talk like this, you feel a little bit more clarity on the science and are a little bit better able to go out into your home, your workplaces, your communities, and have a conversation where we weigh these trade-offs against each other and try to plot a path forward to addressing climate change. So that concludes our talk. If you like what you heard here, if you thought it useful, please tell your friends and family. We're appearing elsewhere in the area through the weekend. We are an all-volunteer organization supported by small donations. We eat a lot of ice cream while we are on tour, and so we need your support. You can donate via the website. We also have a bucket here if you'd like to donate here. And Emma, who's our communication strategist, handing here, you can talk to her. There's also a sign-in sheet over there if you want to receive emails from us or receive the slide deck so you can refer to these images further. And with that, we'll close and take your questions. Thank you very much.
My name is Paula Tracy. I'm a reporter for In-Depth New Hampshire, which is a nonprofit website that mostly I cover the governor and most of the year doing policy information. In the summer, I'm switching my gears a bit to do more science. My two big issues I'm working on right now is carbon capture and climate farms, which is becoming an issue in New Hampshire. We have the largest single property tract that is just placed into the California compliance market. And I thought to try to understand a little bit more about what that role of climate capture is and what level you see something like this benefiting globally. And the other question I want to—
Sorry, can I just clarify, what's a climate farm?
It's carbon capture, where they basically don't cut the trees anymore. And they and you go into this compliance market. Some of them are regulated, some of them aren't.
Sure.
California has it, so if you want to be in the company that gets net zero.
Yeah.
You need to bring down, your, and so you can buy this.
Yes, it's part of like the carbon offset market. This is a tree that would have gotten cut down, but it's not getting cut down, and so it's sequestering carbon. Yes, gotcha.
And so, here we have a lot of questions because the only way people could make money off of the forest is to cut the trees. Now that money is going somewhere else, we're
Yes.
not getting timber tax, our jobs, all those.
Yeah, right.
issues. I don't know if you guys have anything to say on that, and the other issue that I'm also working on is cyanobacteria. And, how global warming impacts cyanobacteria that we're seeing in record levels right now.
Cyanobacteria in the water bodies and the ponds and lakes. Okay.
It's a blue green algae, which has, because of high stormwater runoff these days and the big storms that we're having. Also last year was cooler than normal and the lakes we got a lot more rain. And the washing out process that takes years,
Yeah.
it exacerbated with the heat of the spring.
Yeah.
Fact that we had no ice at all this winter practically on the big lake. They did get the reset, and that these things, including invasive species, are contributing to the whole day.
Yeah.
So.
Yeah. All right, we could spend the whole time just on that. Great. Anyone else? Did you have a question back there? Did I see you raise your hand?
I'm gonna see what the other questions are, thank you.
Okay, good. Anybody else? Yes.
Okay, I'm curious about, the whole switch to, electrical vehicles. And the climate impact of the mining that goes into making those,
Good question.
I'll.
Yeah, okay, great.
Sure, so that's right, to build batteries, we need to extract rare earth minerals. And that is often done via somewhat environmentally destructive mining. For context, rare earth mining is just a few percentage of total mining. So most mining activities, the vast majority of mining activities on Earth for copper and other precious metals, they make up the lion's share. And so this is really just at the margins of the total mining activity. But it's definitely true that there's a direct trade-off there. And right now, there's a big market for prospecting for these new rare earth minerals. So people are looking into previously pristine landscapes to try to begin mining there. There's no way of avoiding that trade-off if we want to build batteries.
I could start. I was just gonna say about electric cars, there's also an interesting aspect which is worth thinking about, which is where that electricity is coming from, how the electricity is being generated. So in the scenario where all the electricity out of your socket is coming from burning fossil fuels, then having an electric car is just a slightly more efficient way of making fossil fuels into forward and backward motion of a car. So so just having an electric vehicle on its own is not necessarily going to be a climate good. And there's that upfront carbon cost of actually just building a vehicle, which can be quite high. So if the people talk about the composition of your grid, so if the composition of your power grid is very fossil fuel intensive, it may actually make more sense at that moment to just keep the old car going rather than splurge on a new car, which will require a lot of upfront carbon cost. And then, so, but as the grid becomes more and more saturated with renewables, that trade-off, that the balance of that turns towards having an electric car. So that's just a wrinkle to think about.
Yeah. To build on that, there's a shared theme between the question about electric vehicle materials, and there's a question that came through in the chat about the disposal of those materials, the environmental impacts of that mining. And so I think in addressing those questions, and also the question about cyanobacteria, it can be helpful to disambiguate global warming from other types of environmental change and acknowledge that we're trying to, chew our chewing gum and ride our bicycles at the same time, right? We're trying to do a lot of things, balance a lot of trade-offs. There's a partner organization to the IPCC, which we cited throughout this talk, called the IPBES, which looks at what humans are doing that causes declines in nature. How do you measure that? It's very hard, but they got a group of scientists together to attempt to do a good faith measure of that. And what they found is that what humans are doing that are contributing to declines in nature, the most important one is habitat destruction. Second is hunting and fishing. Third is global warming, which is roughly tied as well with pollution and invasive species. And all of these activities are interconnected. And when we want to think about how we might pursue a particular solution to global warming, for example, that could end up having positive or negative interactions with some of these other activities. And that's something that balancing those trade-offs depends on our values. And I think moving to the cyanobacteria question, I think none of us are necessarily experts in the cyanobacteria, but it was helpful for you to describe some of the key aspects that were involved with that. And it sounds like that decline in the integrity of those lake ecosystems might also be coming from several different factors, not just global warming potentially being part of it. Certainly the low ice levels is a robust impact of global warming. That, you know, the warmth over the winter we have high confidence that that's reducing ice on the lakes, but invasive species and these other processes are also involved.
Just a little bit more while we have this slide up. For the habitat destruction, I was surprised to learn when we were reading this report that we've drained 85% of the wetlands in the United States. That kind of sets a hard cap on how much global warming can even impact wetlands, right? If 85% of them are not there due to our activities already, we've limited the impact of global warming. The other piece is that sometimes something can be good for global warming and bad for pollution. So remember how we talked about volcanoes putting sulfur in the stratosphere and that led to cooling? Well, coal also is very rich in sulfur. When you burn coal, it's a big source of sulfur emissions. And those emissions also produced a cooling. Particularly before the 1980s when we started an environmental movement to scrub that sulfur out of the atmosphere because it was also producing acid rain. So by trying to clean up the air and remove acid rain, we also removed some of the cooling that was masking the heating from greenhouse gases. So there's a lot of complexity in this web between the cause of ecological decline and climate change.
Just a quick comment about your point about the trade-offs in incentivizing people to leave tree standing and not to forest, and that is, as scientists, I mean, I don't know that I would weigh in on that in one way or another, but I just think it's a great example of the kind of trade-offs that you have to face when trying to take action on climate, right? And there's industries that depend on cutting down those trees for the land, for the lumber, the timber. And so by trying to do something good for the climate, you're negatively impacting the economy and real people whose jobs are at stake. How do you weigh those things, right? The science can't tell you how to weigh those things, and so that's where we as communities have to be in conversation.
You can put you asked how that type of solution of planting additional trees or keeping trees from being harvested, how does that play into the broader global picture? So people have attempted to estimate how much carbon could we take out of the atmosphere if we did a maximally aggressive, keeping lots of forests in place, planting forests in where they might grow even if they don't naturally occur there. And it looks like at the most, this effort, such a global effort, could mitigate something like 40% of global warming.
Present day global warming.
Present day, yeah.
And then once you plant trees everywhere they can go, it's kind of like you played a one-time card. You planted trees and now any future emissions can't be offset because there's no more room to grow trees. The other piece here is that say somebody pays for the next 10 years for that plot of land not to be harvested. 100, right? There's impermanence to that compared to when you burn a kilogram of fossil fuels, some of that CO2 is going to stay in the atmosphere for the next 10,000 years. there's just a fundamental difference between the shorter timescales of forest growth and these millennial timescales of CO2 persistence in the atmosphere. And there's not really a direct equivalence here between burning CO2 with those long timescale implications and committing to something over the next 100 years with a tree.
Yeah, that's where sort of the fossil fuels is really important, right? These fossil fuels are coming from deep underground where they're disconnected from the carbon that's in the trees and in the atmosphere and in the oceans. And there's a sort of natural geological cycles which take millions of years that cycle carbon through that. But by drilling deep underground, pulling up that CO2, we're short-circuiting that geological cycle. And we're introducing new carbon to the system. To cut down a tree or to replant a tree, you're just kind of redistributing it between the atmosphere and the and the land. But fossil fuels are a whole different source entirely. So that's why just planting a tree or keeping a tree from being cut down is not equivalent to not burning fossil fuels. Because when you burn fossil fuels, you're taking fossils from over here that weren't part of our worlds here on the surface and making it part of it.
I think about the carbon capture point kind of plays in a bit here as well. So in terms of the long time scale that carbon dioxide stays in the atmosphere for, so you burn a ton of burn a ton of fossil fuels, some portion has to stay in the atmosphere for a very long time. But we saw from Nadir's plot, once we get emissions to zero, that x-axis went from the year 2000 to the year 3000. If you stop, so this warming is locked in for a very long time unless we, and there are some things like sea level rise, for example, which don't stop rising when emissions stop. They'll keep going up, as long as those temperatures are too high. And so at some point in the future, currently, I think we'd all be very happy if we could just get emissions to zero. I think we'd have a big party and we'd all be like super psyched.
A lot of ice cream.
A lot of ice cream, but eventually you got to think about getting back to that pre-industrial temperature, and for that we're going to need something like, or one of the things that could be part of that portfolio is carbon capture. But currently it's not really a card we can play. So basically, taking carbon dioxide back out of the atmosphere and putting it back into geologic storage is going to be probably one of the tools we'll need to play in order to get leveled off temperature, get back down. Carbon capture will be important for that.
How do you do that?
It's very hard. So I remember right at the beginning, we were talking about how for every million molecules of air, there are only about 400 of carbon dioxide. So it takes a lot of energy to do that. It's a very energy intensive process. Maybe these guys actually know how it's done. I just know that it's hard. But
You basically have a wall of large pans, sucks in a lot of environmental air, and then you react it over a chemical bath to make something like limestone. But as Andrew mentioned, it's the cost of effectively moving enough air through to take out amounts of CO2 that we could even show on these graphs relative to our emissions is way too prohibitive. It's in the billions. I think it's actually in the trillions of dollars right now at current prices. So it's very much in its infancy. That doesn't mean it won't play a role in the future. I mean, technological progress happens, but right now it's not really in our holster.
What would be the biggest bang for your buck to bring down carbon emissions?
Yeah, I think that it's in the energy sector. There are places where operating existing coal plants is more expensive than replacing them with renewables. So you can get up to around 30 or 40% renewable generation of electricity without sacrificing that much. So going beyond that, you run into other problems. The sun doesn't always shine, the wind doesn't always blow. So you need baseload power, and renewables start to be less of a equivalently priced solution for that. You have to make a lot of solar panels, or you have to buy a lot of batteries, and it starts to get more expensive. But getting up to the 40% level doesn't take that much of an additional investment beyond what you would have spent on fossil fuel generated power.
So in terms of bang for the buck, so there's that just conversion of fossil power generation, electricity generation to renewables. And then going along with that, and this is a policy that, you know, is promoted by this recent Infrastructure Act, is electrifying appliances in the home. And so by some estimates, you know, if this is now speaking in America, not globally, you know, that electrifying and even just in residences, there's 4 or 5 appliances that are typically fossil fuel powered, your car, your water heater, your furnace, your stove. But electrifying that can have impacts of say 30 to 40%. So that's why those you know, switching those technologies has been incentivized. This policy. So I think it's another place where there's a lot of conversation happening about getting bang for your buck in terms of our at least domestic emissions.
Just to comment on that, there's often this contrast of doing something at the margin, making a slight change, versus if everybody shifts, if the bulk of people shift. If the bulk of people shift to moving those home uses of fossil fuels to just electricity, then we need to rebuild our electric grid. That then takes societal investment in basically doubling our transmission capacity for electricity. So once everybody starts moving, the whole landscape changes.
I came in late, so I missed what you were talking about, what your mission is, or if you that, but I guess one more question I have is. What would you say to the average citizen, the average education? How do you know, I'm not a scientist, I'm just.
Just at the individual level,
Yeah.
as a citizen.
I mean, I think you know, we don't have particular policy initiatives we're trying to push. We're trying to raise the caliber of the discussion by bringing it in touch with the science and point them to the questions that we think are most important. So that's what we're here to do. Yeah.